So now let's look at dropout now, right? So what are we doing here? We're having input, we are using ReLU activation. We are using ReLU activation and we are adding a dropout after my first input layer and my second input layer, or sorry, second hidden layer. So this is my first hidden layer and this is my second hidden layer. I'm sorry, you have only one input layer always. Apologies for that mistake. Okay, so let's see the code here. Okay, the code is very simple again, right? So we have seen this definition, right? This is my layer one, right? Here first step I'm computing my W transpose X plus B. In the second layer I'm computing the ReLU on top of it. Now once that happens, I'm adding a dropout on the output here. So the way I'm doing it here is I'm computing W transpose plus B, step 1. Step 2, I'm computing ReLU on top of W transpose X plus B. Then I'm adding dropout on top of ReLU of W transpose X plus B. Okay, and for dropout we had this variable, right, keep prob. Okay, so we can set it to whatever value we want. To the best of my knowledge, I think we set it to 0.5 in this case. Okay, so very simple code, right? You're just adding a dropout layer by just because dropout layer is already implemented in TensorFlow for you. Similarly for layer 2, this is your standard layer 2. This is by adding a dropout on top of it. Right? The one key step that you'll notice here is the input to the next layer comes from the output of drop. Look at this. Here we're not saying layer 1. Here we are saying layer underscore 1 underscore drop, which means the input to the next layer, okay, the excis to the next layer are basically dropped out versions. They are basically the resultant of this whole function, dropout of ReLU of W transpose X plus B, right? Except that everything else stays the same for you. The code doesn't change much. Here we'll show you what happens with Adam Optimizer. Again, dropouts are pretty good systems, and if you notice, with each iteration, your test loss and training loss have both moved very smoothly, and you get a loss of 1.480, which is very close to all the other examples we have seen, right? Very close to these values, very close to these values that we have seen. And if you look at the accuracy itself, 97.36, which is very close to this. Not significant difference, right? So dropouts certainly work well. Again, dropouts work well, especially when you have large and deep neural networks or MLPs for that matter. So dropout is also very interesting concept. We have not shown dropout here for SGD, but you can run the code yourself. And that's something that we'll leave it to you as an assignment, right? Because there is a reason why we didn't do it, because it's very easy for you. You can just, it's literally one line of code change. If you just change it from optimizer drop Adam, right? Instead of this optimizer, you just say optimizer drop SGD. You can just define an optimizer. It's very simple. Of course, you have to define the optimizer without doubt, right? So you have your optimizer drop SGD. We have defined this line also for you, right? It's literally one line of code change, and we want you to play around with the code and learn it. Otherwise, if you just listen to these videos, you'll not learn much. Of course, you learn some theoretical concepts, but actually doing it makes a huge difference in your understanding, right? So again, dropouts, just like in other cases, because the data set is very simple, because MNIST is a very simple data set, and we have a fairly simple model. It's not too deep. It's not like 10 layers deep. It's not very complex, and MNIST is a very simple data set, frankly speaking. That's why you don't see huge lift because of dropout, just like the way you have not seen huge lift because of ReLU or because of batch normalization, right? So things are smooth. Don't worry about it. Batch normalization, ReLU activation, batch normalization, and dropouts are some of the most important concepts in modern deep learning.